Before we can start machining our part, we need to review how to measure it properly. In the lab, there are several of these metrology kits, inside of which we'll find a pair of 6-inch vernier calipers, or dial calipers rather. The calipers are a device that a lot of us, or measuring instrument that a lot of us may have seen in the past or may have used, but it's not trivial in understanding how to use them properly. So we want to take 5 minutes and review that with you today. Dial calipers themselves are capable of making 3 types of measurements. Does anybody know what they are? The first type is an outside measurement. If I want to measure the thickness of this piece of material, I use the external measuring jaws for that. The second type of measurement is an internal measurement. Perhaps I want to measure the width of the groove in this V-block. I could use the internal jaws to do so. The third type of measurement is a height or a length measurement. You'll see there's a rod that protrudes out of the end of the calipers as we open them. So if this block was attached to another component and couldn't be removed for easy measurement, I could use this extension rod to measure the height of the block from the surface datum. There's a second set of jaws on the back side of the calipers as well that also facilitates making accurate depth or height measurements. But it still falls in the same category as the extension rod, a height or length measurement. So we've got external, internal, and length or height measurements that we can make with the same pair of calipers. Before we start using the calipers, we need to cover the very basic safety for them. And rather, it's not because they can injure you, but simply because they are precision instruments, and if we don't care for them, they're not going to be able to give us accurate readings, and that means that our parts won't be accurate as well. So anytime we're using the calipers in the lab, we want to do so over a work surface, so there's no risk of dropping the calipers on the ground, which will certainly destroy them. We also want to store them in the blue cases and close the lid whenever we're not using them. That way, if there are chips flying around on the machines, the chips don't get inside the calipers, which have a very precision set of gears inside them, and the smallest chip will destroy the precision of those gears. So always leave the calipers in the measuring box when we're not using them. And finally, the only thing that we use the calipers for are making measurements. Some people use calipers for some interesting purposes. They'll use the sharp corners in order to scribe lines on their workpieces. And some very ignorant people may actually use calipers as a wrench in a pinch in order to grab something and try and provide some rotational torque. Okay? So clearly those are not the common uses for precision instruments, so we're only going to use the calipers for making accurate measurements in our lab. When we use the calipers, there are a few basic things we want to check. First, when you retrieve them out of the box, you want to open the calipers, and in doing so, you want to use the dial. There's a little drum or a little dial that's knurled. You want to use that dial to open and close the calipers. You never want to grab the calipers by their body and fling them open or closed very rapidly, because you're going to send the needle into warp mode and it's going to instantly destroy the calipers. So always open and close them slowly, because it's a mechanical rack and pinion that is actuating the indicator dial on the calipers. So when using them, we're going to open them. We're going to wipe out. Let's say we're going to make an external measurement, which is the most common type. We want to open the calipers. We want to wipe the jaws off with our fingers or a shirt in order to remove any chips or any residue. And then we want to gently close the calipers and make sure that the needle returns exactly to the zero. That means that the calipers are zeroed and ready for use. If it does not return to the zero, open the calipers, wipe them out again, and give it a second try. In this case, the needle is returning exactly to zero. There is a way to re-zero the calipers if necessary. It rarely is necessary. There's a little knob you can rotate, and now the caliper bezel will rotate, allowing you to re-zero the calipers. Like I said, that's rarely necessary. It's usually only the case that you have a chip you didn't realize that are inside the calipers. So anytime you get the calipers out of the box, make a measurement, first step should be to check that the jaws are clean of any debris. After closing them and verifying the zero, we're ready to make our measurement. I'm going to open the calipers. I'm going to measure our work stock for today's part as an example. I'm going to make sure that the part itself is clean and it doesn't have any chips on it. Now we're ready to make the measurement. So I close the calipers over the workpiece, and as I do this, it's important to understand that we always want the measurement when the calipers are normal to the part surface. So if you can see in the video, that's normal. This is not normal. Again, I'm returning normal and not normal. So this is actually the motion that we use when we try and use the calipers. We purposely close the calipers using the thumb wheel. And then as we close them, we will rock the calipers back and forth slightly to find the minimum reading, because the minimum value will be the location at which the jaws are perpendicular or normal to the part surface. If I take the part out and I look at the reading on the calipers, in this case, the part measures 0.5005 inches in thickness, which is believable because this is nominally 1/2 inch by 2 inch bar stock, so 0.5005. And the way that we read that is to take the tense reading off the body of the caliper, basically the ruler part of the caliper, which shows me 5, there's a 5 displaying, so that means 0.5 inches, and then I take the thousandths reading off the dial. The dial tells me one rotation is 100 graduations. Each graduation is 1,000th of an inch, so one rotation is 0.100 inches or 0.1 inches. In this case, I have 5 graduations showing. So that's 0.005 that gets added to my 0.5, giving me a final size of 0.505 inches. Okay. Most of us have used calipers before, as I said. However, there is a particular type of measurement that we all get wrong the first time that we see it. The first time you learn how to use calipers, or this may be the first time that many of us are learning how to use calipers, there's one type of measurement that we are going to miss almost every time. If I open the calipers to an arbitrary size, and I show the students the measurement, I will ask them to tell me what this measurement is, and by looking at the body, I can see a 3 followed by the large 1, so I'm at 1.3, it appears, inches on the body, and I've got 95,000 showing on my dial. So the common response would be that this measurement is 1.3950 inches, which is wrong. The measurement is actually 1.295 is 1.295 inches. The indicator is that moving the calipers, opening them up another 5,000ths of an inch, bringing the needle to 0, will place me on exactly 1.300 inches. So if I subtract off 5,000ths from that, returning me to my previous measurement, there's no way that that could be 1.395 inches. It is actually 1.295 inches. However, anytime you're close to the 0, you have to pay strict attention to whether you are before the 0, meaning you're not all the way to the major tense unit shown on the body of the calipers, or whether you are past the 0, in which case you have reached that 0, or that tense spot. So a little difficult to explain on the perhaps to the camera versus having students here in real time to do so. But I want you to show them a basic measurement on the part to begin, so you can review how to read the tenths digit off the body and then the thousandths digit off the dial. Then I want you to go to some position where it is something with 95 thousandths in it. So 1.395, 0.795, so that you can explain this important point, because it's the biggest stumbling block we all have when learning how to use dial calipers. Finally, after we go through that and we field any questions that the students have, I want to put the calipers back in the box. And then I want the students to rotate through, and I want them to measure the length, width, and height of the workpiece and write it next to the final part dimensions on their drawing, so they know what they're starting with, so they can tell you, is this stock of suitable size to produce their workpiece today? Okay. So while they're doing that, be interactive. Ask them if they have questions. Monitor what they're measuring. You should know that this is nominally 1/2 inch and 2 inch, so it'll make it easy for you to identify when you think somebody's having a little bit of trouble. And be sensitive to the fact that a lot of students are going to claim they know how to use the calipers. but they don't, or they haven't done it so long that it's not a skill that's going to come back to them quickly. So this is a useful exercise. Take 3 minutes, rotate around, have them measure it, write it on their drawings, and they'll make more measurements as we continue making the assigned parts. Because we have to do it frequently when manufacturing parts in a machine shop like this one. Anytime we cut a workpiece with a cutting tool, it's going to leave some sharp edges or burrs that can affect the subsequent operation of machining that workpiece, and also those sharp edges present serious hazards to anybody who later handles those parts. Consequently, we have to deburr our parts immediately after removing them from the machine. The most common method of deburring is to use a file. So I'm going to start by working on this mill part today and demonstrate proper filing technique. When you take the part out of the machine, again, just be cautious that every machined edge can be extremely sharp, so carefully handle the part. Bring the part over to one of the machine vices, or rather the sheet metal vices in the lab. Clamp the part in the vise, and that gives you an extra set of hands to hold the part while you then file it. By each vise, we have a nice array of files, so you can grab one that you think is suitable. We have rough, medium, and fine files for different types of materials. I have a medium file that I'm going to demonstrate with today. And the idea when filing, or the goal, is to put a small 45-degree chamfer along each part edge. Now this piece has been cut on a bandsaw, leaving 4 sharp edges around this top perimeter of the part. I'm going to use the file, but I want to demonstrate some basic terminology. Obviously, we know where the handle is, because all of us have probably used a file at some point previously. But the rest of the file is important to understand because of the way that I'll demonstrate its use today. We have the tip and the heel of the file. So that's basically one end, the point, and the opposite end of the file. The goal, as I said, is to use the file to put a 45-degree chamfer on the workpiece, but it's important to understand that files are unidirectional tools, meaning they only cut moving in one direction. They don't cut moving back towards us. In fact, that just dulls the file and essentially damages the file because you can't resharpen a file. So when filing, you will push the file in one direction, lift off the workpiece, and then return to where you started. You never go back and forth because, as I said, it is going to dull the file. Proper technique is to move from one end of the part edge to the other while simultaneously moving from the tip of the file to the heel. So I'll demonstrate on the edge closest to the camera. I'm going to locate the tip on my workpiece. I'll have 2 fingers on that edge of it. I'll rotate the file to what I perceive is about 45 degrees. And as I file, I'm going to put gentle pressure and move all the way across the file and move all the way across my workpiece. Usually, you'll do 3 or 4 strokes, trying not to push too hard, but you'll be able to see, you'll be able to see the polished surface, the file surface being produced, and your goal is to make that an even surface. That's why you're moving across the file and across the whole workpiece versus trying to file a little bit here and a little bit here and a little bit there. That is bad technique, and it's going to always give you a very wavy, unsightly surface. So again, all the way across from the tip to the heel, and then you want to come around to the other side of the part and do the same thing from the opposite direction. So I'm going to start at the tip on the left side of the part because I'm left-handed. I'm going to move all the way across the part. 1, 2, 3 strokes. And I'll continue on my other surfaces. 1, 2, 3. Visually looking at the chamfer, trying to keep it even. If you want to switch hands, that's fine. 1, 2, 3. Front edge. 1, 2, 3. If you need to, do another one. Again, the goal is to see a chamfer and make an even chamfer. 1, 2, 3. And then the last corner. 1, 2, 3. 1, 2, 3. When you're finished, wipe the part off. And just like inspecting a knife blade, you never just slide your finger across it quickly, because if you did a bad job filing, there could still be a sharp burr that will cut you. So just use your finger to gently brush the part, and then you'll know if you did a good job filing. Okay? You can also hold the part and try and hold the file but it takes a lot more coordination, and the filing is going to go a lot slower because you're putting less pressure on the part. So anytime possible, I highly recommend the use of one of the vices in the lab so that it can hold the part, and then it makes quick work of your ability to file the part, to deburr it rather, in between the steps of using the part in a subsequent machining operation. So the first time, it might seem a little awkward if you haven't done much filing, but you'll see after doing it for 30 to 60 seconds, you'll quickly get the hang of it, and it won't be something that delays your parts during manufacturing. Again, every time you make a part, you want to deburr it for safety and so that you don't get an accumulation of errors, because if your next operation involves flipping your part over in the vise and you have a little burr on the end, exaggerated, that burr is going to cause the part to sit at an angle, to sit sloped inside the vise, and that's going to ruin your ability to hold any type of positional tolerance. Okay. The last comment is that we have other types of deburring tools for circular features. We have what's called a countersink tool. You'll learn how to use countersinks in the lab if you haven't used them already. Essentially, a countersink is just you can think of it as a tapered drill. If I have a circular hole, I'm going to have a sharp edge, just like if I machine a rectangular feature. So the countersink tool, you simply insert into the feature, push on it a little bit, and then rotate it in a clockwise direction. Just like any drill bit or cutting tool, its direction is, again, it's unidirectional. So we rotate in the clockwise direction, and after 2 or 3 turns, it gives us a very nice, consistent countersink and a smooth surface that won't injure anybody and doesn't protrude past the bottom surface now of this feature. And then the last deburring tool is a tool that is used for either deburring straight edges in this fashion. It can put a little chamfer, synonymous with how a file works, or you can use it for deburring circular features by inserting it into the hole and then whirling it around, twisting it around a little bit, and then it also gives you a chamfer. I prefer the countersink because it gives you a more consistent feature, but we like to have a variety of deburring tools because you make a variety of parts. Now that we have deburred and measured our workpiece, it's time to begin the machining operations. If you recall, we're going to finish all surfaces. To start with, we will machine the 1/2 inch by 4 inch length of the part. We're going to start by moving the vise out from underneath the spindle, so we have easy access for loading the workpiece. We'll open the vise and use the rag to wipe the vise out so there are no chips inside it. And then we're going to gently lower the workpiece down inside the vise. Be gentle with that so you don't damage the bottom precise surface of the vise. And in this case, we notice that the 2-inch height of the part is tall enough to extend out of the vise over the vise jaws so that there's no risk of us bringing the cutting tool into contact with the vise jaw. Now I'm going to close the vise, putting about 5 pounds of force on the handle, and I'm going to use the plastic mallet in the lab to make sure that the workpiece is securely in contact with the bottom surface of the vise. And then the last step is to go ahead and put 25 to 30 pounds of force on the vise handle, ensuring that the part is securely clamped. I'm then going to take the vise handle off, and so it doesn't confuse any of us when we're working around all the controls on the machine. Next, we'll load the cutting tool. In this case, we're going to use a 1-inch end mill, just like during last week's training session, and I'm going to use the rag to protect my hand. We'll take the end mill over to the collets on the side of the machine, and I'm looking for the 3/4 inch collet to match my shank diameter on this tool. When I find the right collet, I will know, because it'll be the one that has about enough clearance between it and the tool shank to slide a piece of paper. I take the collet and gently slide it inside the spindle. I then insert the tool shank into the collet, and I set the length of the tool correct. I want to clamp it as short as possible while still clamping on the full diameter of the tool and not clamping on the tool's flutes. When I have it at the height that I desire, I use my other hand to activate the end controls. And once I hear the change in tone, I let the button go, and finally I check that the tool is clamped securely using the rag. Next, we're ready to turn the machine on so we can start cutting. Anytime we do so, there's 3 important checks we want to make. The first check is the speed range. You want to physically move around to the right side of the machine and check to make sure that the machine is in the correct range. We're going to use high range most of the time in the lab, so that's what we want to check for right now. The lever is rotated towards high, so we're good. If it was not, we want to ask a lab TA to change the range for you. We don't let students do that in the class because it can cause an expensive machine repair. The second check we want to make is the clearance between the cutting tool and the workpiece or the vise. In this case, you can see I have plenty of clearance between the two, and we always want to check that before we turn the machine on. The third and final check is the tool direction. We always want our cutting tools to rotate in the clockwise direction as viewed from the top down. So the way that we ensure this is to position our hand on the power switch, identify which rotational direction we will move the switch. In this case, we're in high range, so we're going to rotate the switch to high range. And as we do it, we're going to visually put our eyes on the tool and make sure it rotates in the clockwise direction. Here we go. We turn the tool on. If we're not sure, we turn it back off and wait for it to coast to a stop when we can check, or we can do it a second time. The final check before touching off on the workpiece to set our Z0 is to set the proper spindle speed. We have a speed chart located on the right side of each of the machines. We'll talk about it in more detail during this session, but essentially it's a table that tells us what speed to rotate any cutting tool in a particular material. We're cutting aluminum with a 1-inch end mill, so our speed chart tells us we should rotate about 1200 RPM. To make the adjustment from last week's training, remember the machine must be running. Clearly we can hear it and we can see it, so it is safe to make the speed adjustment. I rotate it to 1200 RPM, and now we're ready to move into position over the workpiece, and then move the workpiece up into contact with the rotating cutting tool. I'm going to get down at eye level so I have a good view of what's going on. I'm going to put 2 hands on the Z-axis handle, and I'm going to rotate the handle to bring the workpiece up towards the cutting tool. I can come up quickly until I am about 1/4 inch away. I'm going to slow down, continue coming up into contact, and when I'm very close, I'm then going to move as slowly as I can by using one hand to gently bump the second until I see the tool make contact with the workpiece. I can see the chips coming off, I can see a halo created on the workpiece, and I can hear the chips as the tool is rubbing over the surface. So I have touched the workpiece, and the last step is to set the Z0 by using the vernier dial. I hold the dial with one hand, I loosen the knurled nut with the other, I rotate the dial so my 0 matches my indicator mark, I tighten the knurled nut, and now I have set my Z0 on the workpiece. With my Z0 set, I'm going to gently move off the workpiece into air next to my part, and now I'm going to set my depth of cut by bringing the workpiece, by elevating the workpiece, in this case 5/1000ths of an inch. Right hand rule tells me clockwise rotation is going to raise the workpiece, so I'm going to move 5 graduations on my vernier dial to cut 5/1000ths off the top of this workpiece. I'm going to use the automatic feed, the power feed that we trained you on last week. And to do so, remember there's a couple important steps. The first is we want to make sure that the dial is set to 0 so it doesn't start suddenly moving. And then I'm going to move the joystick the direction that I want the workpiece to move. In this case, I want the workpiece to move to the left, so I move the joystick to the left. And then the last thing to do is to put your hand on the table, and then as I slowly rotate the dial, the axis is going to begin slowly moving. So it moves over towards the tool. I'm going to move around so I can see when the tool is close to the workpiece so that I slow down and gently come into contact with the workpiece. Now we can see the chips being created. We can hear, if we listen closely, we can hear the sound of the chips. So everything looks correct because it's producing a nice shiny surface on the part, and I can begin to increase my feed speed by just increasing the rotation on the dial. And I'm going to cut all the way across the workpiece, keep my hand on the table to sense for vibration, and I'll come all the way off the other end of the part. Once I'm off the part, I'm going to rotate the dial back to 0, which ceases motion on the power feed. And the last step is to return the joystick to the neutral position. Since the entire top surface cleaned up on that cut, we're ready to stop the machine and remove the workpiece. So we turn the machine off securely with 2 fingers, wait for it to stop, and now I'm going to move the workpiece away from the sharp cutting tool. Grab the vise handle and open the vise. Once I've done that, I can remove the workpiece and take it over to the workbench for deburring. Now that we've deburred our part and rotated it 180 degrees in the vise, we're ready to cut the second side. The part is the exact same thickness as it was when we took it out of the vise, so there's no need to reset Z0. We can simply move the part up another 5/1000ths of an inch in order to cut 5/1000ths off the second side of the workpiece. We're going to do our 3-step check once again. We're going to check the speed range. I'm still in high range. Check clearance between the tool and the part, and I'm going to check the direction of the tool as I turn the machine on. And now I'm ready to continue with the cutting. If I move to this side of the machine and bring the tool close to the part, the tool obstructs my view of the cutting zone. So on the mill, it's often necessary to move around so you get the best line of sight, so you know when you're close to the workpiece. In this case, I'm close to it, so I'm ready to move over and resume my use of the power feed. I'm going to set it to 0. I'm going to move the directional joystick, the direction I want the workpiece to move, and now I'm ready to start to rotate the dial slowly in order to begin making contact with and cutting my workpiece. I see the shiny surface, I see the chips, so I can increase my speed and replicate what I did on the first side of the part. When I'm finished, I'll make sure I let the tool come all the way off the workpiece and then rotate the power feed knob to 0 speed, finally putting the joystick back in neutral. Now that we took the part out, deburred it, and measured it to make sure that it was in tolerance, we're ready to move on to the next pair of sides. In this case, we're going to cut the 2" by 4" surfaces next. If you recall, during the equipment training, we needed something to align those surfaces parallel to our XY plane. We used parallels for that purpose, but before I put the parallels in, I need to remember to wipe the vise out every time. So I've got the parallels. I'm going to load one at a time, very carefully and gently. I'm going to lower them into the vise so that the sharp corners don't mar the bottom surface of the vise. So gently lower the parallels, set the workpiece on top, and close the vise, clamping on the workpiece. Put 5 pounds of force on the handle, grab the mallet, tap the workpiece securely against the parallels, 25 to 30 pounds of force on the vise handle, and finally, we're going to remove the parallels so we don't damage them while machining, and return them to their proper storage location. We're ready to do the facing pass on this side, which means we need to set our Z0 once again, since we're working with new surfaces. We do our 3-step check for the tool. We check the speed range, we check the clearance, and we're going to check the direction. Now I'm going to move the part over towards the workpiece. I have to stop and lower the workpiece. Move underneath the tool. And once again, gently come up into contact with the rotating tool. As I get close, I'm going to slow down and use the tapping technique while looking at the clearance between the tool and the workpiece. I can hear it, I can see the shiny halo, so that's my new Z0. I'm going to set the 0. I'm going to move off the workpiece, and then I'm again going to increment my depth of cut another 5/1000ths of an inch. And I can move over to the power feed, moving my head around so I can see when I'm close. This time, making an adjustment in the Y direction so that a portion of my tool overhangs the rear edge of the part. And lastly, I'm ready to engage the automatic feed. I set the speed dial to 0, move the directional control, hand on the table, and then gently begin moving the tool into contact with the part. I can see the chips, I see the shiny surface, everything looks good. I can pick up my speed, and in this case, cut all the way across the workpiece. Move all the way off. Turn the speed control back to 0. Joystick back in neutral. And now I'm going to move over in the Y direction, overlapping my last cut. And I'll repeat the same thing in the opposite direction. Speed knob to 0. Directional joystick, the proper moving to the left. And then I will gently come into contact with the workpiece. And then pick up the speed. And in this case, I have a 2-inch wide workpiece and a 1-inch diameter cutting tool, so that's going to require 3 passes to face the top surface of this workpiece. Again, I allow the tool to come all the way off, stop the speed, joystick in neutral, index over in the Y direction, bring the tool close to the workpiece, speed control on 0, joystick correct direction, and then gently come into contact for the third and final time. When I'm finished, I'll move all the way off the workpiece, a safe distance away, turn the speed control knob to 0, joystick in neutral, and then turn the machine off with a firm hand. We took the part out, we deburred it, and we've rotated it 180 degrees and loaded it back into the vise. This time, however, we are overhanging the left side of the part about 1/2 inch from the side of the vise jaws, so that after we face the top surface, we can come in and easily cut the next surface in sequence. Since the part is again the same height as it was when we cut the first side, I can simply raise the part 5/1000ths of an inch, and now I'm ready to make the next cut across the top surface of our part. We do the 3-step check: range, tool clearance, and tool direction. At that point, we're ready to begin cutting. I'm going to move up close to the part. I'll move over to this side so I have a better line of sight. And once I'm close, I'll go ahead and activate the power feed. Again, speed control to 0, directional joystick, the way I want the table to move. And then I slowly rotate the dial and I watch what's going on between the tool and the workpiece. I see the cutting action. I can pick up my speed. And just like on the first side, cut swiftly across the workpiece. I'm going to take 3 cuts once again. Each time, letting the tool come all the way off the part, stopping the axis feed, putting the joystick in neutral, and indexing the tool over so that I overlap the last cut that I made. Gently coming into contact each time, and then picking up speed. Letting the tool come all the way off the workpiece each and every time. Speed control to 0, joystick in neutral, index the Y-axis. You'll notice each time I do it, I need to look perpendicular to the direction that I'm moving. And now we're going to make the third and final pass on this second part side. Gently move into contact and then increase the speed just like we have on the last 2 passes. Once again, all the way off the part, speed knob to 0, directional joystick in neutral, and turn the machine off with a secure hand. At this point, we have two remaining unfinished surfaces, the left and right side of our workpiece. I intentionally overhung the left side of the vise so that I can reach the left side of the workpiece without bringing the cutting tool precariously close to the hardened steel vise jaw. In this case, I'm going to turn the machine on and touch off in the X direction using the side of the tool versus the Z direction using the bottom of the tool as we did previously. Before I turn it on, I follow our three-step check. For speed range, I'm in high range. For tool clearance, I have plenty. And finally, for tool direction, we'll watch the tool and make sure it rotates in the clockwise direction when I turn it on. Then I know I'm set to do my machining. I'm going to move the tool up into contact with the workpiece, putting my head in between the two so I can see when I'm close and I know when I need to slow down so I can very gently come into contact. That's key anytime we touch off. Gently, I made contact. Now I'm ready to come over to my digital readout and zero the X axis at that location. That's my X datum now. And finally, I'm going to use the Y axis to move the tool out of contact with the workpiece. In this case, the tool is just rubbing the side of the workpiece, barely cutting anything. I move off the workpiece into air, and now I'm ready to set my depth of cut and actually make a cut on the left side of my workpiece. I use the right hand rule, which tells me to move the part to my left, I need to rotate the handle in a clockwise direction. I watch the DRO so I know how far to move the workpiece. I'm going to cut about 20 thousandths off. And I'm going to move around to the right side so I have a better line of sight. I'm going to put my hand on the table and then gently bring the tool again into contact with the workpiece. When I'm close, I slow down. So I very gently engage the workpiece every time. And as I pick up the speed, I can't feel any more vibration. So I can move across the left side of the part fairly swiftly. I move all the way off the workpiece into air, and now I can move around to the power switch and turn the machine off with a secure hand. Now we remove the part, we deburred the end that we cut, and we've reinstalled the part with the uncut end facing the cutting tool and overhanging the left side of the vise once again. The idea here is the saw cut, the way the material comes to us, being cut on a bandsaw, does not provide two ends that are perfectly parallel to each other. So that's why we're doing these light 20 thou finish cuts in order to produce two ends that are parallel, allowing us to take a valid measurement of the part's overall length. So repeating what we did last time, three-step check, speed range, tool clearance, and tool direction. We turn the machine on, come over into contact gently with the side of the part. Once we make contact, we zero the digital readout in the X direction. I'm going to again move off the part, move the part over, so I'm cutting 20 thousandths of an inch off the left side of the part, hand on the table, and gently re-engage the part as I make the cut across the left side. I can't feel any more vibration, so I can cut pretty swiftly across this side of the part. I move all the way off the part. I turn the machine off. And this time, I'm going to leave the part in the machine and bring the measuring calipers to the part. I will wipe it off first. So I'll bring my rag, being careful of where the tool is. And now I'll use the calipers. So I check my zero, I open them slowly, put them on my part, and at this point, I will obtain an accurate reading of the part's overall length, which is 4.130 inches. So we have approximately 130 thousandths of an inch left to remove off the left side of the workpiece. Before I move anything, I'm going to reset my digital readout. Now I'm going to turn the machine back on. Last week, during the equipment training session, we told you that the maximum material we can remove in one pass is 100 thousandths of an inch. So I can move over 0.1 inches towards the tool. I'm going to use a little bit of oil now because this is a larger cut. Everything up to this point has been a light finish pass. So I'm just going to put a little bit of oil on the part. Put my hand on the table, a safe distance, of course, away from the tool, and then I'm going to re-engage the workpiece gently. As the chips are coming off, they're going to be warm, but they're not going to hurt me. If I want, I can stop, and I can use the chip guard on the machine to prevent the chips from hitting my hand if that's uncomfortable. And I continue the cut now. Nice and slow, using my hand for vibration feedback. Have to cut slower when we're cutting more material like we are now. I come all the way off the part, and again, I want to take approximately 130 thousandths of an inch total off my part. So I move it into position, and I make my last cut now, the last 30 thousandths of an inch. Gently into engagement. Trying to move very fluidly across the part because I don't have a power feed on the y-axis. So I just have to move it as smoothly as I can in my hand. All the way off the part. Turn the machine on. And now I can get my calipers and make my final measurement to ensure that my part is within the allowable tolerance. Now that we have all of our part sides finished and cut to length, it's time to do the remaining end milling operation on the part. If I look at the part drawing, you can see that involves cutting this little step into the left side of the part. To do so, we need to set two part zeros or part datums. We need an X0 and we need a Z0. The X0 is very easy to set because we haven't moved anything, so we are actually at the right location to set our X0. So we simply zero the digital readout in this location. That gives us the X0. For the Z0, we're going to turn the machine on and touch off on the top part of the workpiece once again, just like we did previously, and that'll give us the second required datum. Before I do it, I'm going to move away from the vise so that I can do the three-step check of speed range, tool clearance, and tool direction as I turn it on. Now, I'm going to move over towards my part. I need to lower my part and then move the tool above the part. Having done so, I'm going to establish my Z0 by raising the part towards the tool, and once I get close, I'm going to slow down and very slowly, very gently come into contact by using this one-handed bump method. And as soon as I establish contact, I'm going to stop and zero the Z-axis vernier dial. Now that I have my Z0 set and my X0 set, I can move off my workpiece and commence with the cutting. If we take a pause and look at the drawing quickly, the overall height of our part is 1/2 inch, and the slot ends up being half of that, leaving a 1/4 inch material left on our workpiece. Since we're removing a 1/4 inch material, we have to use multiple depths of cut, just like we taught during the training sessions. So we're going to do two 0.1 inch depth cuts, followed by the remaining material. I'm going to move around to the front of the part, and I'm looking to make sure I have plenty of clearance between the tool and the vise. And I'm going to move all the way over and make my first cut, the one that's farthest to my right. I'll explain that in a moment. So essentially, we're going to finish at exactly 2 inches, but I'm going to leave a little bit of material, about 20 thousandths of an inch, for a finish pass at the very end. So I move over to 1.98 inches into my part, and I'm going to set the X-axis table lock, so that way my part doesn't vibrate around while we're making these heavy roughing cuts that we're about to do. I'm ready to start with the first cut, so I need to raise the part 0.1 inches, so I get down at eye level, just to do a quick check that I'm in air. And I'm going to watch my vernier dial. I'm going to rotate in the clockwise direction to raise my part, and I know it's the right direction because the numbers are increasing when I rotate in that direction. So 20 thousandths, 50 thousandths, 75, 100 thousandths. I'm going to carefully apply a little bit of oil to the workpiece, keeping my hand far away from that rotating cutting tool. I just need 3 little strips of oil. Finally, I'm going to move around so I have a good line of sight. Put my hand on the table, get down eye level so I can see when I'm about to engage the workpiece, and now I'm ready to start my cutting. So gently come into contact. Again, if I want to use this chip shield, I can do so. It blocks the hot chips from hitting my hands. Hand on the table, gently into contact. As I pick up speed, I'm sensing the vibration with my other hand, and I pick a speed that is just below the point that I can feel the machine begin vibrating more. I cut all the way across. I come off the back side of the part into air. Now I have to remember to release my table lock. I move over a little bit. Again, I'm going to take 3 cuts with this 1-inch tool. So I move over a little bit, overlap. The last cut, if I want to, I can re-engage the table lock. This time it's not so important because I'm going to keep removing all the material to the left side of the part. So if the table moves around a couple thousandths of an inch, it doesn't matter. But I just like to get in the habit of using the table lock whenever I'm making a heavy roughing cut on the machine. So I gently come back into contact. Then I can begin to pick up my speed. You can see the chips are a lot larger now because we're trying to remove as much material per unit time as we safely can. All the way off the part, release the table lock. I move the X-axis over a little farther, making sure that I'm going to be lined up to cut that last portion of the workpiece, re-engage my table lock, put my eyes in so I can tell when I'm close to the part. So once again, I gently engage the part, and then I can pick up my speed. All the way off the part. Release my table lock. Now I'm going to come back, return over to my 1.98 inch location, or close to it, within a couple thousandths. Re-engage my table lock. I'm going to check and make sure that I can safely raise the part another 100 thousandths. I'm going to put 3 more strips of oil, just enough to keep the chips from wanting to weld or stick to the cutting tool. Hand on the table, come up close to the part, and then slow down and gently engage the part each and every time. Then I can pick up my speed. And cut all the way across the part. Release the table clamp. Move the part over. Re-engage the clamp. Gently re-engage the part. And continue with this technique until I have removed the 0.2 inches from the top of my workpiece. All the way off the part. And then we're going to turn the machine off. I'm going to release the table lock for the last time. I'm going to move the tool out of the way so that I can bring the calipers back to the machine, back to the part, and actually measure it to verify how much material remains to take off this workpiece so that we end up achieving the tolerance, the desired tolerance on the drawing. So I move it out of the way. I use the rag or the compressed air to blow off the part in the vise. Use the rag to wipe off the part. Being careful because some of the edges on the part will be sharp. So use the rag, protect your fingers. Now I would ask, I would grab a pair of calipers, remembering to check their zero, and measure the part with the calipers. In this case, the part is measuring 0.295 inches, which is very close to the 0.3 inches we expected it to be. So that means we have about 45 thousandths remaining to remove from this top surface. So I bring the part back towards our tool. We generally like to leave 20 thousandths of an inch or less for a finish pass. So if we want to cut 45 thousandths off, then I'm going to turn the machine on. Make sure I have clearance. Check tool range and rotational direction. Turn it on. I'm going to leave about 20 thousandths at the end. I said we have 45 thousandths left to go. So I'm going to make my next cut of 25 thousandths depth of cut. A little bit of oil is reapplied to the part. I always like to stick my head in and make sure that I'm well above the vise jaws every time I move over the vise. I'm going to move back to my 1.98 inches. And lock the table, lock the x-axis. And make my cut the same as I did last time. Gently moving into engagement and across the part. Releasing the table lock, indexing over and Y, checking how far I move over, re-engaging the part gently. You can see I'm feeding more quickly now because I'm cutting a lot less material and I don't sense any vibration. And at this point, again, it's completely optional whether or not you want to use the table lock. I'm not using it on this last cut because there's no risk if the part moves to the left or the right a couple thousandths of an inch. Come all the way off the part. At this point, I should have 20 thousandths of an inch remaining to cut off my part. So I'm going to actually move over to my final target location in the X direction, 2.00 inches. I'm going to lock the table lock because this is an important cut to me. And I'm going to raise my, my workpiece the remaining 20 thousandths of an inch. But first, I check and make sure I have plenty of clearance between the bottom of the tool and the top of the vise, which I do. So I move this up another 20 thousandths of an inch, and this should be my last cut and my finished cut. So 3 little strips of oil once again. Hand on the table, eyes where I can see the engagement of the tool as I near the workpiece, and then slowly ramp into engagement as we have so many times before. I'm going to feed a little more slowly now across the part because this is the last cut. It's my finished cut, so whatever finish ends up on the part is going to be what's visible to anybody who sees the part and what's functional to anything that gets clamped to the part. So I release my table lock. I move over in the X direction. I make my second cut across the part. Coming all the way off the part once again. And I repeat the same thing for the third and final pass. Putting my eyes in here so I can see what's going on. I can see that I'm close, so I know to slow down and gently engage the part. And then pick up my speed. All the way off the part. And at that point, reach up with a secure hand and turn off the power switch. At this point, we have finished all the mill work on the part, and it's time to proceed to the drilling work. We've removed the end mill, so it's time to grab the drill chuck. That's what we're going to use for any drilling related operations. We've gone through the standard sequence to properly remove the last tool, so we're ready to install this one. The first tool in sequence is going to be the edge finder, which we need to demonstrate its use. We open the drill chuck. We install the edge finder. You'll notice that the bottom of it is spring-loaded. It's fragile, so be gentle with it. The easiest way to explain how it works, as I said, is through demonstration. So we're going to move the edge finder around to the right side of the vise, which means I need to lower the part quite a bit. I'm going to move around to the right side jaw. Okay. The edge finder is meant to rotate about 1,000 RPM. So I do my standard check, speed range, tool clearance, and then tool direction. And I'm going to make an adjustment to the spindle speed to bring it down to, again, 1,000 RPM. When we're using the edge finder, you only use the lower cylinder, which measures exactly 0.200 inches in diameter. And we begin by pushing that lower cylinder slightly off center. So it's meant to rotate in an eccentric fashion. If we just gently push it off center. We also raise the part so the portion that we are trying to locate and set as our datum is going to contact the lower cylinder. So in this case, my vise jaw comes to about halfway up the small 0.2 inch diameter cylinder. So that's a good height. I turn it on, and then I move the edge finder towards the surface I'm trying to set my zero on. As I come close, the eccentricity decreases. I continue moving in the same direction as slowly as I can. Keep moving, keep moving, keep moving. And at just the right instant, there it is. I will see the edge finder move out perpendicular to the direction of the surface I'm trying to locate. Okay. At that point, I come over, I set my zero on the DRO. I like to always check it twice, so I use the right-hand rule to gently and slowly move away from the part, and then I will reapproach the part. I see the edge finder trigger, and I can look at my digital readout and see that I'm well within 1,000th of an inch repeatability. So I'm happy with that use of the edge finder. The last step when using the edge finder is to move away from the workpiece. Again, you must get used to using the right-hand rule and moving slowly. I move away from the edge finder, and then I will lower the part. I will come back to my zero using the digital readout and continue moving the same direction, an amount equal to the radius of that lower cylinder. In this case, it's exactly 0.100 inches. And then I must re-zero the digital readout, and that places the center line of the spindle exactly in the plane, in this case, of the right-hand side of this vise jaw. Okay, so I have set my X0 datum to coincide with the spindle center line, and I could then measure over 1 inch or 2 inches and place whatever holes I want to with respect to the vise. I've shown you how to do it on the vise. Now I want you to look at the drawing, determine where your X and Y datums are, and set them on your part using the edge finder. After you use the edge finder to locate your part zeros or your part datums, the last important check is to move the machine into its 0, coordinate location, or close to it, and then lower the edge finder down to the part so you can visually verify that the center line of the spindle is in fact aligned with the two planes, your X plane and your Y plane. If you forget to offset for the radius of the edge finder, which is 0.1 inches, or if you offset in the wrong direction, this quick visual check is going to tell you that before you end up putting the future features in the wrong location. After using the Edge Finder to locate our 2 part datums, we're ready to commence with the drilling sequence. The first tool in the process is called a center drill. The center drill is a special tool used to accurately begin drilling a hole. If we compare a center drill to a traditional drill of the same size, we can see that the center drill has a lot more favorable length to diameter ratio, which is another way of saying it has a lot higher stiffness than a traditional drill, and that's what's going to ensure the accuracy, or going to improve rather, the accuracy of our hole placement. We've loaded a center drill into the drilling chuck, so the next thing to do is to set the rotational speed. I'm going to do my standard check for range, tool clearance, and rotational direction as I turn the machine on. Then I'm going to reference my speed chart, which shows me for a 1/8 inch diameter drill, the rotational speed for cutting aluminum is approximately 1600 RPM. So I'll adjust the machine while it's rotating, while it's running, to 1600 RPM. I'll lower the center drill to gently contact the workpiece, and that gives me a little target where I can place a few drops of oil, and then I can return to the part and very gently bring the tool into contact, drill a little bit until I see a chip coming off, and then I'm going to use a pecking process where I drill a little bit and I retract. I drill a little bit and retract. That evacuates the chips and helps keep the tool a little bit cooler. With the center drill, we need to drill approximately a depth of approximately the drill diameter. So in this case, I'm going to peck until it looks like I've drilled about 1/8 of an inch into the workpiece. And finally, I'll raise the spindle and move the part into position for my next hole. Now that we have reviewed the tap and drill chart, we've loaded the appropriate tap drill for the 1024 UNC thread that's specified on our part drawing. In this case, the tap drill size is 0.157 inches in diameter. We retrieve that drill from the appropriate drill index, load it into the drill chuck, and now we're ready to finish drilling this hole all the way through. The rule of thumb for drilling is we can step up in 1/4 inch increments. So in this case, the 0.157 is smaller than a 1/4 inch, so we can go right from the center drill to this final size of 0.157 inches. I will turn the machine on after performing the 3-step check for speed range, tool clearance, and finally tool direction. I will look at the speed chart that is posted on our clipboard, and for the 0.157 drill bit, this tells me that the appropriate speed is roughly 1400 RPM, so I will make the adjustment. I will use the oil bottle to put a little bit of oil in the crater created by the center drill, and then I will commence with the drilling process. So I come down gently, I touch the part, you can see the chips coming out, and I'm going to peck drill, making each drill depth or each drill peck approximately equal to 1/2 of my drill diameter. Again, the goal of peck drilling is to allow the chips to come out of the hole. As I drill all the way through, I'm going to feel it, I'm going to feel the drill break through in the air. I will retract the drill, retract the spindle, and then move into position for my next hole location. In this case, it's 3.5 inches. And I'll repeat the exact same sequence. A little bit of oil, and then gently come down towards my part, begin the drill process, and then peck a distance equal to my drill radius. The next features are the countersink holes in our part. We've loaded the appropriate size clearance drill based on the information presented in the tap chart. In this case, it's of diameter equal to 0.196 inches. If we go to the speed chart on the machine, that tells us that the speed should be approximately 1200 RPM for this drill. So I do the 3-step process: range, tool clearance, and tool direction. I turn it on. I adjust the spindle to 1200 RPM. I'm going to use the oil, and then I'm going to use the peck drill method, making the pecks again equal to roughly half the drill diameter. This part is pretty thick, so as I get halfway through, I'm going to retract the spindle and put another few drops of oil inside the hole. and then finish the hole using the peck drilling method. Once I'm through, I'm going to retract the tool. I'll complete the 4 countersink holes, and I also have to remember to use this as the intermediate size drill for the center hole that will eventually be reamed to 5/16 of an inch. The final feature on this face of the part that requires drilling is the center hole through which the motor shaft will mount when this part is in use. If you look at the part drawing, the 5/16 hole has a very specific tolerance associated with it. It's called out as 5/16 of an inch plus 1/1000th of an inch to plus 2/1000ths of an inch. That's to ensure that we always have a clearance fit with the motor shaft, but it is a very close clearance fit, meaning there's a very small amount of clearance giving us a precision mate. In order to achieve such a tight tolerance, we will use an additional tool. The drills are very good at producing, they're very efficient at producing holes. However, a tool called a reamer can give us a more accurately sized hole. So that's what we're going to use to finish this feature. So the reamer has 6 flutes on it compared to 2 flutes on a typical drill bit. And it also has a lot larger diameter core. So what that translates to, again, is a hole that has a lot better dimensional tolerance than a conventional drill bit. However, when using the reamer, we can only use it for a very small finish pass. What that means is we always have to take the finish size of the hole, or the size of the reamer, and we subtract off 1/64th of an inch from that size, and that gives us the final target hole size with which we want to drill the hole before we can use the reamer to finish the hole. In this case, we've got 5/16 or 0.3125 inches minus 1/64th of an inch, which is roughly 15/1000ths of an inch. And if we look at the drill box, the closest drill to that size is about 0.298 inches. So that's the drill that we've loaded and the one that we're going to use to finish drill this hole before we use the reamer. We have a through size hole from the previous pilot drill. We put a little bit of oil. We turn the machine on. We check the speed chart. We adjust accordingly. And now we're ready to drill the center hole size. We're going to peck drill, just like we've done before. All the way through, retract, and we're finished. Now that we've drilled the hole the correct size in anticipation of using the reamer, we're going to use a 5/16 reamer to finish drill the hole to size. In this case, 5/16 is, according to our speed chart, when we're drilling a 5/16 hole in aluminum, the target speed is roughly 700 RPM. But the rule of thumb for using a reamer is that you rotate about half the speed that you would for a comparable size drill bit. That would put us somewhere around 350 RPM. However, on these machines, the low end of high range is 500 RPM. So for convenience, we're going to use that. We're going to use 500 RPM since we're working with aluminum, which is an easy material to drill and ream. So I'll turn the machine on. I'll make the speed adjustment down to 500 RPM. And as we begin the reaming process, we'll take note that the reamer itself is much longer than a typical drill of the same size, and that's intentional so that the reamer does not influence the size of the hole. It simply cuts it to the exact size that the reamer was manufactured to. I bring the reamer down to the part, and I feed it very slowly from the top to the bottom. There's no need to peck because I'm removing such a small amount of material. I simply want to move it at a consistent feed rate all the way through. I can feel when I'm all the way through it. I retract it, and I turn the machine off. The remaining features on this side of the part are the 4 countersinks required to properly accommodate flathead screws in this component. Flathead screws give you clearance for closely located objects, so it's actually a common screw that's used in industry. The bottom of the flathead screw has a chamfer, and to create that chamfer in the workpiece, we use a tool called a countersink. So I've got an example here. I have a different size loaded in the machine, and that's what we're going to use to create these countersink features. The countersink itself, we're going to rotate about 500 RPM, which is actually where we are from using the reamer in the last step, so we don't need to make a speed adjustment in this case. I'm going to turn the machine on after the 3-step check: range, clearance, and direction. I'm going to bring the countersink down towards the part after I make sure that I'm in the correct location, and I am, 0.5 inches, 1.5 inches, I bring it down close to the part, I gently touch the part, I can see the chips coming off, and finally, I'm going to put a little bit of oil on top of the part. I'm going to use a peck motion, just like we learned previously. I'm going to do some pecks. And in this case, I have to reference the drawing to understand when I have created this feature properly. It tells me that the countersink hole should be opened up to approximately 0.42 inches in diameter. And we're going to iterate a few times using a pair of calipers for measurement to check when we have reached the right size. And there's a reason we're going to do it this way, so that we can show you how to use one of the accessories on the milling machine. So to check the part, to check the feature, we wipe it off. We retrieve a pair of calipers. As always, we check the 0 on the calipers. In this case, we'll open the calipers to the final size of 0.42 inches, and we can lock the calipers there. And then we check the size of the feature. And in this case, I can see that the feature is still undersized, it's still small. So I'm going to return the calipers, turn the machine back on, put a little more oil on the part, and I'm going to open up the countersink, or I'm going to make the countersink a little bit deeper. So I'll do a few iterations each time, turning it off, waiting for it to stop, wiping it off, and checking its size with the calipers. In this case, I'm very close. One final peck. And I am to size on the countersink feature. If I grab my flathead countersunk screw, I can bring it over to the part, put it in location, and then I can check for the clearance, make sure that the head of the screw is flush or slightly recessed with the surface of the part, as it is in this case. The last step, and the feature that I wanted to show you, and the reason I did it this way, is the depth stop on the milling machine, or the use of the depth stop. So to use it, you wipe the tool off, you wipe the part off. Notice everything is stopped, of course, as it should be if we're going to touch anything. And then we lower the tool gently into contact with the workpiece, so into the contact with the countersunk feature we just created. And then we bring up the spindle lock and rotate it into tight engagement with the spindle. So now we can move into location for our next feature, which in this case would be 1.5 inches over. We're close to it. We can turn the machine on, put a little oil on the part, and we simply use the countersink tool until it stops moving. So the depth stop is going to prevent us from going too far. When we can't go any further, we know that we have finished that feature to the exact same height as the first one. We turn the machine off, we could check it. In this case, we're confident that it's correct, and we can move into the location for the third and fourth countersinks. The final features on this side of the part are the 4 threaded holes in the left side of the workpiece. These holes, as previously noted, are 1024 UNC threads. To create these, we retrieved a 1024 UNC tapered tap, meaning the end of the threading tap has a taper. That's always necessary when you're creating threads from just a drilled hole. And we've inserted that tap into a tap handle, which is what will allow us to provide the rotational torque to produce the threads. The final component that we use is a spring-loaded tap guide, meaning it has a point on the end that is spring-loaded, and it engages a hole in the back side of the tap handle. So the way the system works is you load the tap guide into the spindle, you move the spindle into the location for the hole that you're about to thread, and then you insert the tap handle and tap into place, and now the spring-loaded tap guide ensures that the tap is perpendicular to the workpiece surface, or coaxial to the axis of the hole that we drilled previously. We're going to use our oil and put a lot of oil on the threads on the tap, and then we're going to use our hands to rotate the tap And at the same time, we have to lower the spindle to keep the spring-loaded tap guide in contact with the backside of the tap handle. So now as I rotate the tap, I'm going to start to feel more resistance, in which case I back up about half a turn, and then I continue in the forward or clockwise direction. I rotate about a turn or a turn and a half, and I feel more resistance, and then I back up about half a turn. I continue to do this because it breaks up the chips into small, manageable pieces, and it maintains the integrity of the thread that I'm producing. So forward, 1.5 to 2 turns, and then backwards half a turn. So continue through the workpiece. And just like with drilling, you'll feel when the resistance drops and the tap exits the bottom of the workpiece. And you're going to have to maintain, again, contact with the spring-loaded guide. So you constantly have to move the spindle up and down when you're using the tap guide. Now, I can feel very little to no resistance, meaning the tap has threaded all the way through the workpiece. So I'm going to grab the air, the compressed air, and I'm going to use it underneath the part to blow off the tap, to blow the chips off the bottom of the tap before I retract the tap through the workpiece. So now I'm ready to reverse it and retract it. So I rotate it backwards with one hand while raising the tap guide with my other, keeping it in contact the entire time. And once it stops raising, it's a tip off that you reach the top of the thread and you're ready to pull the tap towards the tap guide, pull it off the part, and continue on and move in position for the next hole. Now that we've completed all the other features, there's only one left on the workpiece. And we're going to use that as an assessment of your understanding of all the processes covered up to this point. We want you to load the workpiece into the vise in the orientation shown in the drawing. We want you to leave the center hole that we finished with the reamer previously visible so that you're able to check the intersection of your drilling and threading tools with that hole. And then you're going to go through the sequence of using the edge finder, the drilling tools, and the threading tools to create and thread this intersecting set screw hole. At the very end of that, the TA will cover the addition of one new tool, a bottoming tap, and they'll explain at that point the purpose of it and when we use it.